It must be separable. No, it's nonlinear. We can't even solve it that way.
But if we want to find the half-life, we must know the initial conditions.
The doctor said the entire eastward must be quarantined.
Atlas, prepare the ship for emergency landing. This nebula's too unstable. Okay, crew, today we got to cover the differential equations so that our laboratory can safely navigate in outer space. We need to make sure that our resources are stable, we need to make sure that we can predict the weather, and we need to make sure that there's no catastrophes and disasters. So let's get started.
Autonomous equations are going to help with stability. So let's start with a dy over...
We're going to change this to a red dt, and that's going to be equal to a y minus y squared. We can see that this is autonomous because the variable we're using to differentiate here, which is t, is not actually present in our equation.
Our resource consumption is going to be governed by separable equations. But we can tell that the autonomous
This equation is actually a separable equation because we can put the y's on this side. We can say 1 over y minus y squared dy is going to be equal to, well, we could put dt on this side. And at this point, the idea is that you want to integrate both sides. This one with respect to the y, and this one with respect to the t. These are separable. Now in general, a separable equation would have some sort of t expression, so maybe you would have a t over here with a dt, but then this would not be an autonomous equation.
Well, since we're dealing with radioactive materials, we have to understand linear differential equations.
So I'm going to write a couple of examples. We'll start with a y, and I'm going to take a triple derivative, and then we can go ahead and add plus 2 of, let's put a y with a double derivative, and then we'll go plus. Now the reason that this is linear is even though we have a whole bunch of derivatives here, the y itself has no exponent, it's just y. And then we can have any function of x, some crazy x's, we can have other constants in front, but this is just a linear differential equation. Let's just remember that if we wanted to take these derivatives, we could say that y prime is equal to simply dy over dx, but then y double prime would be equal to d squared y over dx squared. All this stuff up here is still linear. Once we get into the nonlinear,
That's going to help us with predicting the weather as we're navigating through the nebulas. So let's see if
we can make some examples. We'll start with a y prime is going to be equal to y squared, and that's why it's not linear, is because there's a y squared plus x. All the other stuff doesn't matter. We could also use the second derivative, so we could have y double prime is going to be equal to, well, we have something like e to the y prime. That's not a linear equation. And then we could add whatever we want over here, plus 3y. We could try going into y to the triple prime, so that would be something like, I don't know, y times y double prime plus sine of y. But really the reason why it's not linear is because of these particular red sections. This stuff right here is totally okay. It's the red stuff that makes it not linear. And one final example is going to be y prime, but let's say we squared this for some reason. Well, that would simply be something like d over, or dy over dx, but then this would be squared. And this is not equal to y double prime. This is y prime squared. Now let's make sure we know how to verify solutions
in order to maintain stable controls and have accurate simulations. So let's
try something like d squared y over dx squared, second derivative, minus 5 times dy over dx, plus 6y is going to be equal to 0. Now let's say we were given the solution. So we're given y equals e to the 2x plus e to the 3x. And all we have to do is to check to make sure that this is the correct solution. What we need to do is we need to start taking derivatives here. So we're just going to go y prime is going to be equal to 2e to the 2x plus 3e to the 3x. Then we can go y double prime is going to be equal to 4e to the 2x plus 9e to the 3x. At this point, all we need to do is we need to take our second derivative right here, take our first derivative right here, and our y, and we're just going to plug them back into the original equation. So the second derivative, first derivative, and y. Let's see if we do that. We would get something like 4e to the 2x plus 9e to the 3x right here, minus 5 times the first derivative, which is this, 2e to the 2x plus 3e to the 3x, and then plus 6 times the y, which is going to be e to the 2x plus e to the 3x, and then we have to try to add that all up. The question is, does this all actually equal 0? And if it does, then we verified the solution. So let's see, it'd be something like 4e to the 2x, and you get minus 10e to the 2x, so it's going to be like negative 6, plus a 6e to the 2x, so that gives us a 0 right there. And let's do that for the 3x, so 9e to the 3x, and then minus 15, that gets us to negative 6, and then we have another positive 6 over here. So we're at 0 and 0. This is 0.
In order to maintain control over nuclear chain reactions, we need to understand doubling time and half-life.
So for the doubling time, the amount of some sort of stuff at some particular time is going to be equal to 2 times the initial amount. Similarly, for the half-life, we could say that that stuff at some particular time is going to be equal to half of the initial amount. For simplicity, let's imagine we had 100 galactic credits. Now, we'd like to grow these credits to 200 credits, but in order to do that, we need some sort of an interest rate. So we're going to multiply this by some sort of percentage over the years, because, well, we get 2% per year. So we have percentage per year times the credits. Now that's going to give us some sort of a units, so we're going to get credits over years. And if we wanted to represent that in terms of a differential equation, we could say something like dn over dt, because n is simply units of credits, and t is the units of years. Next year, this is going to be 110 credits rather than 100 credits. So every time you calculate this, you have to use the current value of credits that you have. So in order to represent that, we're going to say that, yeah, we have this interest rate, but we're going to just multiply it by the current n that we have. Not the initial n, but the current n. And so now we have our expression over here, dn over dt equals r to the n, r times n. If we try to solve this equation, we're going to find that the amount of credits that we have at any particular point is going to be equal to the initial amount of credits times e to the power of rt. Now, this particular equation has no limit. So if we were to plug in t of infinity, we would actually get infinity here. So just keep in mind, this has no limit. Now let's do some checks. Let's say we want to figure out the number of credits we have at time 0. So all we need to do is plug in 0 over here for t, and we get e to the 0 power. So this just turns into 1. And we find out that we just have the initial amount at time 0. Well, that's great. Now let's say we're in exponential growth here. So we're going to go up 30%. So what that really means is that we're going to get 1.3 times the initial amount, right? We went up 30%. And so now if we try to plug in n of the infinity, it turns out that, well, again, we're going to get infinity here. We kind of mentioned there's no limit here for growth. Well, let's say we wanted to decrease by 30%. And so that would mean that at some point we get to 0.7 times the initial amount because we decrease by 30%. And we would also imply that at the infinity point of time, we would reach 0 for the quantity over here. So we'd have to probably adjust this r to be a negative r in order for this to happen. But we just want to make sure that this is for growth up here, and this is for decay. Now, if we actually tried to solve for doubling time and half-life time, it turns out that they're actually going to be the same. The time to double equals the time for it to reach a half. And the answer is actually ln of 2 divided by the rate. And this is actually be true for every single situation, as long as we have this particular form right here.
Just in case we have some kind of an epidemic on board, we need to make sure that all our crew members are
trained for emergency procedures. So let's imagine we have the spaceship, which has a certain amount of crew inside, and we introduce one infected person. Well, then that would just simply mean that the population of our closed environment here would have increased by 1. That means that we just have one sick visitor, and if we try to plug in I of 0, just the amount of infected people at time 0, that's just going to be equal to 1, and the amount of susceptible people at time 0 is going to be equal to the P closed. With this in mind, let's formulate the equation for our susceptible population, which is going to be something like ds over dt is going to be equal to negative beta times si divided by P total. So this is the infect rate right here, and then this is going to be the number of susceptible people, the number of infected people, divided by the total population. But really what's more important is the infected equation. So let's say di over dt, the number of infected people over time, is going to be equal to the positive beta here. And again, this is the infect rate times SI divided by P total. But usually there's going to be some sort of a subtraction here, some gamma factor, because this is the number of people who recovered. Now, in the infected equation, we have a positive beta because more people are being infected, whereas over here we have the negative beta because now there's less susceptible people since they're already infected. Let's also consider the recovery rate, which would be something like dr over dt is going to be equal to that gamma factor times the I. And this is, again, the recover rate. Obviously, this is going to be positive, and it's going to take away from the infected population here. So these are sort of the three equations that will represent the epidemic.
Oh, excuse me, Commander.
Huh? What, Atlas?
It's just that what you were saying, this reminds me of designing robots like myself and predicting future enterprise success rates.
Fascinating, Atlas, but we need to stick to the curriculum. We're just doing theory today.
Oh, but understanding real-world application can inspire curiosity in our pupils, Commander.
You have a point, Atlas. It can be more relatable, but we need to stick to essentials.
Oh, absolutely, sir. I'm here to complement, not disrupt. Perhaps I can merely showcase some of my abilities, bridging theory with practice.
Yeah, that might work. Let's include some of that with the basic training module. Prepare some blueprints to demonstrate the application.
Certainly, sir. They'll be available by the end of the mission.
Okay, great. You heard him. We'll have to wait a bit to get access, but we'll be digitalizing the materials along the way, so make sure to keep up with the latest updates. Now, back to what I was saying.
Clearly, we're going to need some powerful temperature regulation because in outer space it's going to be pretty cold.
So let's make sure we understand Newton's law of coolings. We have something like dt over dt, and this is temperature over time. This is going to be equal to some sort of constant times the temperature minus the room temperature. If we want to solve this, let's make sure we have to separate this out. So we have 1 over T minus T room on the left times dt, and that's going to be equal to K times dt. This is the temperature, and that is the time. Then we just integrate both sides, integrate over d capital T, and integrate over lowercase t. We'll go into solution techniques in the next video, but right now, let's just realize that this would give us the t as a function of time over here. It's going to be equal to C E kt plus t of the room. And there's 2 points that we can usually use to find these constants C and K. We usually use that T 0 time, the temperature at time equals 0 is going to be equal to the initial temperature, T naught. And we also usually use that T at infinity, the temperature at times infinity is going to be equal to the room temperature.
While we're out in outer space, we need to have good air and water purification systems. So
Let's try to figure out how much salt in kilograms is going to be inside of this tank right here. Well, at the beginning, we're going to have just 100 liters of pure H2O. So in the beginning, we are going to have 0.
The dynamics of my
salt in this
movements are
tank.
represented by
However,
differential
we're gonna have an
equations.
influx here
And think of the
where
climate
there's
models
sort of
for a journey ahead.
rate of salt water that is being pumped into here. And this is happening at some sort of liters per minute. We also have the mixture is being poured out of here, so the R out really is this mixture in here, and that's also happening at some liters per minute. Let's assume that these are going to be equal, so that way this is a nice consistent problem. What we know is that as time starts to reach infinity, we're going to reach the max tank concentration. And that max tank concentration is actually going to be really, really similar, or basically equal to the input concentration. And that input concentration is going to be in, kilograms per liter. So we can get an idea of the maximum amount of salt in kilograms that's inside of the tank. Because we can basically say that the concentration of the input concentration right here, which is the concentration in the tank, right? That's going to be some kilograms over liter. Well, we can multiply that by the total volume of the tank itself, which is going to be in liters. The liters will cancel and we'll get kilograms of salt inside the tank. What about the concentration of the tank itself at any point in time? We can figure that out by knowing the kilogram of the amount of salt inside the tank, but then we divide that by the total volume. So usually we don't know the amount of salt, so we're just going to label it as A, and we know that it's some sort of kilograms, and we divide that by the 100 liters. And so this sort of kilograms over liters is the concentration of the tank at any point in time. Now we can figure out what's the net rate of salt going through this tank. So we're sort of say dA over dt. And we know that this is going to be kilograms divided by minutes, right? So let's see. Let's try to first figure out what is the input. So the input is just going to be concentration going in, which is going to be in some sort of kilograms per liter. And then we have to transform the bottom side from liters to minutes. Well, the only way we can do that is to go back to our in rate. So we're going to multiply that by R in, which is going to be liters per minute. And now we have kilograms over minutes, which is the input rate. Okay, now we have to subtract the output rate. So let's go ahead and figure out what the concentration going out is. Well, remember that the concentration really going out is the concentration of the tank. So it's really the concentration of the tank, which is the mixture right here. And that's going to be in some sort of A kilograms divided by 100 liters. And then we have to multiply that by the R out, which is just some liters over minutes. And, well, there we go. We have our equation.
Now we can safely navigate through the nebulas in outer space while maintaining control of our resources and without running into any catastrophic disasters.